Today, Dr. Feng will give us a keynote speaker. The title is Multi-Scale Modeling Simulation Landscape of Gas-Solid Flow in Gas Fluidization of Particle Mixture and in Blast Furniture Raceway. Now, Yiqing, it's your time. We keep your time around 40 to 50 minutes. Yes. We have 20 minutes question and comments. Okay, welcome.
Okay, thank you, Professor Wang. And good evening, Beijing and in China. Also, must be good morning in UK and other countries. And it's with great pleasure to present my work. And when Haigang approached me for a presentation, I think over in multi-phase flow, a so broad area. Actually, I start to think my career almost working in this area over 20 years. So what I should pass the information. So I started with the work from my PhD work. This I finished in 2004, nearly 20 years. The work probably I have some story to share in my PhD. I struggled a lot, and indeed probably some of the understanding still valid. One is my PhD is at the University of New South Wales with Professor Abby Yu, world leading scientist. Probably most of you knew him. And the work is in DM CFD modeling of particular multi-phase flow. The thing is, for this part, this is all my PhD thesis. I cannot. I want just pick some of the key part. One is we knew the multi-phase is any phase consists of discrete particles and the contained gas with strong interaction. Very broad research area with many industrial applications. Certainly a very intensive research area. During the 25 years ago, when I visited Professor Yu as a visiting scholar from China, supported by China Scholarship Council, and I saw some very interesting phenomena. Cannot click it. I found when click it, it will broken and just check it. This is from experiment from the book of particle technology from Professor Martin Rose. They can be bubbles and then slugging and spouting, very complex phenomena. In the 1970s, and Professor Professor Gildat categorized into A, B, C, D different phenomena. I'm not going as details. Here is the once why we call CFD. If you look at the history, just put a slide there, think of the governing equations, two types. One is we call Newton law. They say that, and developed in 16th centuries, almost 400 years ago. And after 150 years later, they come to another way. Actually, we both can describe the flow of the objects. One is we call in the discrete or Lagrange method, Newton law or particles. Another called Navier-Stokes equation. Navier-Stokes is the age. All say far away, but only with the computer power is available, such as from personal last thing from personal computer. And probably the young guys cannot remember 286 to 586. This is almost 30 years ago. Then parallel, then GPU now is the more advanced one. This makes the flow numerically possible. And then the computer modeling area we can see with two types of focus. One single phase, the focus is mainly on turbulence. The average Navier-Stokes or large eddy direct inverse situation over 100 or even 1,000 of different type models. This is for even for single phase. And if for industry related to our area, process industry, this is mainly focus on multi-phase, the strong focus on the strong interface interaction. And this is YHFD, I don't need to tell them. Then this I saw this about the equations there over 100 years, a number of 100 years. But only recent 1990s, you see, have a 2-3 type model in all both here is in 1990s. It's available to solve the multi-phase flow use computers, such as start to work as first is from the middle. For the gas solid flow, we can treat the particles use the discrete method, use Newton law, and the gas phase or the fluid phase use the local average control volume method, and the coupling through them. And then another is pioneered by Professor Gedasmo is we both solid and liquid, solid and gas phase treated as a continuum approach by solving the traditional CFD method. On the other way, we can treat the detailed flow over each particles, and then the particle fluid interaction force not needed to use the Argand equation or that kind of algorithm. I can use the integration of the flow pressure and skin friction over each particle. The left side is very, very computing demanding, and the right side is cannot get detailed information. Right in that state, the middle part we call DEM CFD modeling received great interest. I actually at the right time to join Professor Yu in 1990s, in late 1990s. And my PhD topic is on the blast furnace raceway and the subsaturation in a binary fluidized bed. And I just quickly go to this animation generated using computer so over 20 years ago, but still it looks not quite can tell a lot of information. This is 2 types of particle. The red is a large, such as 2 millimeter, and the green small. Once fluidized, they start to, at a certain range of velocity, they start to segregate with small particles fluidized at the top and the large particle at the bottom. Here today, I'm not going into the details of the flow pattern, just say at that stage, what I struggled in my PhD to work on this area. One is the model development and validation. And the model development, the coupling between the two is like this: from discrete particle, we get the velocity, porosity, then calculate the drag force, and fit to continuum approach. From continuum approach, we get the random number of each particle, then get the individual particle force fit to the discrete particle. And but for the Gamma equations, one struggle is actually for the gas phase, it's just the single phase Navier-Stokes equation multiplied by its porosity. But Professor Gedasmo proposed in his book in 1990s, he put a very popular book. He proposed 3 models for the Gamma equation, A, B, and C, such as in model A. And the pressure shared by both phases. Model B is just put into the gas phase. Consequently, for the solid phase, use discrete method, translate 2 types of translation, 2 types of motion, one is the translation and the rotation by these 2 equations. We focus on the translation movement, the gas particle interface force. To consistent with the model A and the model B, they have 2 types of way to calculate it. And these 2, and if we further direct, they got some difference in the middle term. This means the pressure, when the pressure shared by 2 phases, and another is in model B, we don't have pressure term. And what's the difference is the coupling scheme. This early stage is the first paper is actually just separately. This means the gas phase and the solid phase they tackle separately, and this makes not necessary to satisfy the Newton's law. This is the reaction force and the interaction should be equal. Another is from the once realized the later paper, they get the force for the whole control volume control cell, then divided by the particle in that cell, and then feedback for individual particle. And this makes satisfy Newton's cycle, but the particle in one control volume will get different direction. This makes not that logical. Another way proposed by Professor Yu and the team is we calculate the force for each individual particle, then summarize that, then feed into the control volume. This way, they can, you see, scheme 1, separated the first paper by Professor Suji, cannot satisfy Newton's third law, also cannot be logic. And while the second one, they can satisfy Newton's third law, but not logic. And the third one, this can satisfy both. That means this one gradually received and accepted in the late papers. And this particle fluid interaction force, certainly we have early stage use Professor Gedas's model, actually Eigen equation and Wien equation, and combined together with different porosities. And then later, develops use a continuous approach. You see Eigen equation, you get not consistent at the porosity 0.8. While you develop, they get smooth. And later for this one, we have many other works, such as I'm not going. It's as a coach Hill use to get other formula. Another is the Professor Hui-Lin Wu with Professor Gedatbo from the use the stitching function of this part and get it more smooth. This is the way the work. Such as in that time in 2003, when I finished my PhD, I summarized the modeling work only in model A and model B, based on the coupling and based on particle interaction force. At that stage, only 20 or 30 papers in this area. That's if we have PhD students, you can say at this stage, we can say when we talk about DM, we talk about different, we can be thousand and countless papers. Why I thought this way is, you see, and this is the later paper by also by my Professor Yu team, my supervisor team in 2007 in chemical engineering, a review, very good review paper. You can see at that 2005, the increase rate, and I reckon at the moment, so in this area, it's still fast growing. So why I still say 20 years of work, so many people work this area and with computer get more complex. I still want to share my knowledge and my study in this area because during that, but I struggled a lot to get some new understanding. Maybe this is still, I reckon, my understanding is still valid. When the in Model A and Model B, it's a long-standing topic in Professor Gedasbo. He mentioned the Model A is ill post and the Model B is well post physically. When I visited Professor Gedasbo, he still talk about this almost in 1997 or 2007. And this is actually in Model A and Model B for mono-size particles, they almost no difference. Both from his PhD student use two-flow model or recent work, while in recent work by Professor Colin something group, the careful with his PhD student, he found he published paper in chemical engineering science in 2002. He said deep Model A and Model B make a very big difference. When Professor Yu forward this paper to me, I first I checked the paper. I found he used different setup make the one. One is when I restart this one, we can see model A and model B, and exactly very similar. We cannot justify the difference. Why is the difference he made? His initial packing, his model A used a very little bit slightly dense packing, while model B used a relatively a little bit slow, loose packing. This small difference gets the better expression different. So after that, we published a short communication to chemical engineering science, and then I'm not going the details of the argument with Professor Colin Salting, but this is no difference. Like this, use this we call comments to the paper and the paper written back. If you have interest in this area, you can find it from us. While later, when I work it on the multi-size particle, we found model A and model B really make a difference. Model A, you see the particle gets the segregating pattern less than model B. And this is another velocity. And with high velocity, almost off that bed, but still model B get some more segregation than model A. And what's the difference? Then I start to do an experiment, use the same geometry and operating conditions to the simulation. You see, this is the experiment snapshot use the video camera. And then you can see the flow pattern, the small particle on top and the light color of the large particle at the bottom. And then after that, from the flow pattern qualitatively comparison, just a visual use eye, we can see model B close to experiment. Meanwhile, I use the bed freezing method to capture layer by layer of the solid and measure as user save to get the weight concentration. We get the concentration profile of the height. You can see model experiment the black one. Model B get a close match to the experiment that model A, and they at a different velocity. I'm not going to. So why got such a difference? This is the picture. Probably I spend some detail to explain. You see model A and model B. What's the difference? Actually, the difference is actually the part of the how to treat the particle fluid interaction force. Model A and model B, the difference in the middle part. In the part is model B not shared by the the traditional, not have the traditional pressure term, but it's this term the drag multiplied by its solid volume fraction. Actually, for that term, why model B? Model A is a term usually when we talk about the pressure, we normally think is a static pressure, such as the object in water, you got a bouncing force. That's why. While this make a difference, this makes the result if analytically stay a fixed bed, we can see model A at different porosity and model A, the 2 millimeter particle in my simulation, and get large drag than small particle. While model A get more difference than model B, this one. While we see this is the absolute value, actually the difference not by its value, is the value divided by its mass or the gravity. It means that it's acceleration. If based on this way, the small particle get large value drag than the large particle. And after this way to express the result, we can the difference between small and large particle for model B more than model A. This makes the simulation model A get more segregation than model A, model B. This so far we can explain why model A and model B make a difference. The second is which is the logic, which is the more reasonable. An experiment explained this one is model B is better. Why? Let's see what I can put with you in next slide. You see the pressure drop. Let's use a sketch because the particle exists now at the same superficial velocity, the large particle system get the pressure of PL and get the pressure drop less than small particles. But when they are mixed together, the contribution of the small particles get more contribution than the large particles. While based on model A, is the pressure drop shared by the volume fraction. That means like a buoyancy force. If the same volume, they should get a same share. But in reality, the small particles, if the same volume, they get more contribution than model than large particle. So it's fair should use the small particles should share more drag. Then the model B is does not have this issue compared with model A. After that, we do one more simulation. If this is not good, and if you use model A, the pressure not shared by volume fraction, it could be the contribution such as by its surface area. And then you can see model B get the result, model A get the result. Sorry, close which shared by surface area get a result close to model B rather than with the volume based on model A. And you see this model A, model B experiment. And if we choose model A, but the pressure drop shared by surface fraction rather than up to now, I saw model A make I can conclude make minor difference in bond size particle, but for multi-size particle, model B is favored, and so far I am very excited. I and almost finished my PhD and but this is not what I discussed. A and B is partially right. Later we see A and B. If very complex phenomena, though we use a approximate method to do it, actually in reality, we really don't know how the contribution of small and large particle, such as the flow over each particle, not uniform. So when I worked in Saro through vacation student, we do a direct numerical simulation. That means to generate many particles, about 1,000 particles, and to get detailed flow over each particle to see how the share of the small and large particle. And meanwhile, my professor at him working this use the latest version method and get detailed a new model. This is in 2014. That's in chemical realm. I believe in this area. This is so far to my understanding the well advanced drag model for multi-size particles. So that's why after that we use the model to do a lot of microdynamic analysis, such as the velocity distribution. That's how it works, and the contact force and the drag force, and the in different direction. Did a few publications. This is my PhD publication. The citation as the prepared probably 2 years ago, and recently I get more published. This one talk I talked about is share some of my PhD experience in DM type modeling. They extend to discuss the direct numerical simulation. When I joined Saro, mainly working in industries, actually we do a lot of work in the DM type modeling cannot satisfy the demand. This type. For example, I use this one to show two work in using two fluid model, such as this is a chemical looping process. The aim is for what? For CO2 capture. This is one. Another is for chemical looping for what? For hydrogen production through fuel reactor and steam reactor and air reactor, the methane and through the endothermic change to hydrogen, and then from the further the hydrogen produced through steam reactor, then the oxidize back again to get the M means for metal oxide from its original form in the fuel reactor, and then go through the air reactor back to the original form. This means the metal keeps the same, but through this oxidize and reduction process, we convert the methane to hydrogen. This so far I talked about the three type model, but this still some process not satisfy the demand. This why if the particle type model so expensive, why we can use little propose another model called cost green model. Cost green model means we use each particle represent a lot of particles, such as this is the sand experiment. This another twin circulating fluid bed video working. How do we DM explain why a true fluid model cannot get a reasonable recirculation rate? That's why we call cost green model. Another we call what? Called multi-phase particle in cell method, a Barracuda type, and each particle represents a group of particles. And then this is work use this model. And I'm not going into its details again. This type model to this published about 10 years ago. Then later, when a student from Tsinghua University approached me, he wants to do what? We say for co-beneficiation fluid bed, such as dry separation. That means a fluid bed with fine particle, with we put the coal and ground with coarse particle, and the fluid bed like a buoyancy force, the heavy one, and sink to the bottom, and the coal and the light one flow on the top. And this one, people approached me to do PhD project. I thought, so far, none of the current model we can work in this area. And even you see the underground coal cutting and drill to get a different size of particle, or even for the granulation process, such as the power for pharmaceutical industry. And we have three together the fine powder and the great big particle. Realistically, we need to model it, use the large particle to capture the accuracy. We use the DM type model, and to save time, the media term fluid one, we need to use the two fluid model type. But so far, no model couple them together. This is when Qinggung approached me. You see, at the 2015, the type model we can summarize to can be both two fluid model and even two fluid model. If the greater further cost, we can use the cost grid model here. And then if we use the DM, but we want one particle represent a lot of particles, we go the multi-phase particle cell. Then up to 2005, this is all type of the model available. And then when Qinggu approached me, we suggest him to couple the two models together. We call two fluid model DM hybrid model. And this is a result when he was here to do. I hope it works. Yeah, you see, the fluidized bed media fine particle will two-phase model approach or use the regular method, and the large particle use DM, and then the density, high density, heavy one sink at the bottom. It's simply like floating over the water. Just we call this dry separation, and the large one on the top. And Qinggung certainly did a good work, and he has some background before joining me on DEM and two-phase model. He quickly get this work done in 9 months. Stay here, and he want to finish it earlier, and initial period, 1 year, he actually stayed annual and published 2 papers, one in Chemical Engineering Journal and another in Chemical Engineering Science, and quickly accepted. So that you can understand quite normal, and almost no the editor quickly accepted it. And then after that, that's why I talked about, I speak a little bit quick, just tell here the story about the different type of models and the model I involved in the development. But in terms of application, when I joined the thyro, particular minerals, it's more complex. None of the model can do it. Let's show you some of the work in thyro. This is from another slide. Apologize, I did not combine them together. Hopefully, it's still I can do it. This is a type of dust presentation I prepared last year for the minerals in the mineral area. Minerals is take this chance. I thought I still have probably 10 minutes. I want to give some examples this year. Just in this case to introduce a little bit about thyro. We are working in thyro and for Commonwealth Scientific and Industrial Research Organization. And this is the schedule of the almost 100 years. And with over 50 sites. And I mean, in the mineral, it's all the different organizations covered almost everything, similar to Chinese Academy of Science. This is the promote to thyroid. This is the globally used Wi-Fi. Actually, is a technology from thyroid, and also the we call the polymer or the banknote, the money here. Also over 30 countries use it invented by thyroid, and the other not going into detail. And from the mineral, let's say from the original rock, big particle, and through a series of different improvements to the all concentrated, that's from the crushing and comminution, and then flotation, shaking the, and then to the concentrate, all concentrated, such as for the further smelting, such as iron ore for the hot blast furnace, aluminum for the element smelting cell, different particle, flash smelting, and electronium, different material. And then the processing industry, indeed, multi-physics, very complex flow, and important bulk commodities. That means a small improvement, I mean the big saving. I still have try to finish in 10 minutes for the work. And then I'm not going into detail the one. That's we can say the plant is the large scale can be by kind of meter. While in detail to the molecule level, we can have in between them we magnify. We can say with the process unit turbulence eddies for the type error, and then to the multi-phase with the bubbled particles and droplets, and then even very fine particles that's decreasing length scale. While for the time scale, and the process equipment can last for months, but the resident time in a process unit can be by hours, and the mixing time by minutes, and the reaction can be very quick by seconds, and the combustion, such as a coal company, can be the nanosecond. How to say, how do we link this with computational modeling? this is if we can focus on the plant scale, the thing is we care, and the from plant to the molecule of individual particles, we can decrease this scale. But for the information from the information flow from the micro model, we need for a modeling approach, we need the detailed modeling such as the molecular level, so the individual molecule or the Monte Carlo Hotmail. Then we can get the fine particles, we can model the other population balance or DEM type modeling, bubble drops such as use free surface type modeling, and turbulence certainly we use CFD, traditional local average control volume CFD approach and process unit. And then here is here I use last one I use introduce the different type model, but my present title also use the word multi-scale. That means we cannot model all the information, all the scale information in one simulation. What we do is from the industrial scale, we only concern about the competitive, how to make money, run process efficiency, and environmental friendly. We need to find the problem, and then we develop a realizable model, that micro or the process scale model, local average model, and then to satisfy, meet the industrial needs. And meanwhile, the macro model, there are some uncertainties such as the closer correlation, such as complex serial granular flow. We need to further develop models from micro type model, such as bubble particle, like the DNS model for the packed bed to improve the drag, this kind of type model, and then this kind of circle or loop we call multi-scale model. Certainly in China, we another popular one, pioneered Professor Jing Hai Li about mesoscale, actually, macro scale, ranking not between the macro and micro level. And this, why I saw here, I mentioned this, I just want to say, you see, use we call DEM two-fluid model, hybrid model for co-beneficial fluid bed. But when I approach the mineral approach such as a second mill, it's more complex than that. Second mill with what is we use a rotating drum to get the steel ball and rocks and lift up and fall down, and to make the rock break into small slurry. This is a very, very complex process. And again, for this one, if we use the two-fluid continuous approach, cannot get the detailed impact between particles. If we use the use DM type model, and then the fine slurry, we cannot model it at current computing power. Then the one proposed in 2015 that as a hybrid model is a key for this kind of simulation. While this is several vacancy student from Northeastern University, and when here we develop model, of use Euler type model in Fluent, while use DM type model. Why I saw the if we couple them together, then we can meet the model the second mill process. While another problem encountered is in Euler type model, actually the model is based on kinetic theory of granular flow. It's at that stage mainly worked for what? For dilute phase or fluidized bed. But when we model it for the mill process, which dense packing of the bed, the kinetic theory not that accuracy. Then we through the students through we linked the solid pressure and solid viscosity, linked them with the porosity, and do propose a new model, and the model can get such as based on the dilute phase, intermediate phase, and dense phase, use different type models, and to solve that. Once get this done, then further apply it to model the couple of them together. This one I did not update the model This is based on fluid. There's a gas phase, continuous solid phase, and describe this type of model. What this model is simply a model. What we want to do for industry, we need a solution, such as you see, ideally, when a ball or the second mill, we want the particle lift and fall down. We don't want the particle fall down direct to the lining material. That's why they got what? Get a strong wear of the lining material. While the particle, we don't want to without follow too low. If too low, this the interaction is not strong. Ideally, we want the particle lift up and fall down to this region. That means get enough impact, also not where the not break the lining materials. So, but this is the profile of the lining material. But you see, new liner 1 month, 2 months, after 2 4 months, it's different. The service life gets different profile. So how to keep this model always in a reasonable flow pattern is difficult. So we need to link them together with the industry, such as this picture of the original liner and the different stage of wear. That's too different. So we linked our model. We model use hybrid model to model different stage of the wear. So see, this is a sketch to show the particle flow pattern. You see, once as the new lining material, we use 1 power, and once the wear, because with strong wear, we need to increase the rotating rotating speed to make sure the flow pattern always in a reasonable shape. This is one way we link with the model with industrial application. This is for the hybrid. Probably I have one more to discuss the further one. Once the particle grind to fine one through hydrocyclone and then to another process, what we call, not going to the flotation. Flotation, what's the process? We use once the particle move into a cell, we generate what we call bubbles. Once the hydrophilic particle will, like water, philic love the water, then stay in the liquid, while hydrophobic, that means dislike the water, and then attached to the bubble and then lift up again. This is why this will have so many fine particles, and with the bubble, we can never use the DM type model to do it. That's why. So what we do for this complex process, we develop a traditional shifting model. That means we get the whole flow pattern and then use the traditional shifting model to see the design, whether they are design flawed or such as a short circuit and then or dead ruin and this type. Another is the recovery of the particle. How do we judge it? We use link the model with such as the detailed we develop. This is still the bubble and the flow model. Develop what we call link the bubble particle collision efficiency related to the bubble size, the turbulence. This is the big component, and then use this type of model based on macro, the local average turbulence and the bubble concentration and the solid contribution. We work out how much particle collision efficiency and the collective efficiency, and this link together work for different industries. And meanwhile, the bubble particle collision model based on a lot of assumptions. We use macro that may develop the detailed DEM type model to see the whole particle sliding time, collision efficiency, and then use that to improve the analytic model, such as the popular one, Shu and GSE, and with CFD can get similar range, but get improved accuracy, and then feed this back to the continuous approach to get the industrial assessment of the performance of different design of the fluidisation cell. Actually, another one is I'm not going to detail into the second one. Probably I stop here and maybe quickly to the conclusion. Oh, sorry. Okay, great. Yeah, that's right. Processing industry are multi-scale in nature and need multi-scale modeling and current computing speed. And multi-scale is a development technique where micro-scale calculations are used to develop correlation, which then fit into the macro-scale model. But the multi-scale is very case dependent. There can be a sequential, that means we develop one model to fit into the another model, or they can be concurrent. That means we use the DEM and two-field model combined into one model. And also we need a physical experiment and American model to combine them to best use of each of the type. And certainly it's a challenging and fast-growing research area. We would have a significant impact of a wide range of scientific and engineering modeling disciplines. And I'll probably stop here, and Professor Wang and other probably I'm happy to answer some questions to share. Yes, thank you.
Okay, thank you, Dr. Feng. The time about 50 minutes talk. It's very intriguing, also very nice talk.
Yeah,
from fundamental model to some application typically used in industry. Actually, there are some questions from the audience. Maybe you can notice from the message. Can you see the message from the message?
Yeah, yeah.
Yeah. The first one is Yan Qing Song. He want to ask about the evaluation, maybe the purpose and the concept of cutting grid compared with traditional structure or unstructured grid.
Okay, let me read the question. Song, yeah, Yin Qiang Song, right? Yan Qing. Okay, the last one. Professor, how do you evaluate?
The first question.
With traditional structure, unstructured grid. Okay, very interesting. Yeah. How do you evaluate the pros and cons of Cartesian? I actually, to be honest, I did not involved in this area. To evaluate, you should to compare with experiment. And good example is you just use the standard of small case, so many use based on the PIV or this or the type of modeling to get the detailed flow and result, and then to validate, to justify which one is better. To be honest, I did not do much in the CFD area for the comparison. And I read another one is 9737. Thank you, Professor. It's not model, take advantage of both model A and model. Yes, to be honest, when I'm a little bit hesitant whether I should still talk about model A and model B, because when I have one slide to tell, when I finished my PhD, I conclude I favor the model B. Actually, later we can find when someone asked me, I thought, either model A or model B. You use model A, you use model A drag type. You use model B, you use model B type. It does not matter. Actually, you see, even the pressure shared by solid volume fraction surface fraction make a difference. But the thing, the flow in through different sides, it's not uniform. So that's why later Professor Abiyu proposed a new drag model. That drag model actually is used in model A. Why I still use A and B is for convenience of my discussion. Also at this stage, I saw in another word is to give you some in Chinese, I'm not sure in English how to抛砖引玉吧. This that share my strugglings. Hope that can get you some what kind to critical thinking. This is just a way of critical thinking, not just a follower, because everyone uses model A. We will use model A, and I think it's case dependent. Better use right drag formula.
Yeah. Also, here is another question about the model A and B, down to different size scale of particles. So.
Sorry.
Yeah, another question from Yanqing Li.
Yes.
That the present models A and B adapt to different size scale of particles. Maybe he also use to different particle size.
Let me open the. That's why when this area actually not many people seriously assess the difference between model A and model B. That's why they got this problem. Actually, in Professor Gidasbo's book, he used 3 type model, A and B, and AC not here. My thinking, if you read my paper in this area, it's later another from my supervisor team with a KV2 also published another paper still talking about model A and model B. If you read this paper, let me see, in chemical ASHE, I have a paper in 2004, assessment different model formulation. You see, the justification is if this uniform size of the particle, the flow around each particle, we can share the drag uniformly by its volume or surface, it does not matter. But if different size, if you share the pressure drop, it's been on the contribution. Its contribution is a small particle get more contribution. It should share more like this. But in reality, not always like that. In reality, if the particles, such as the small particles, small particles get large drag, but the flow will get less flow through the small particle. We will get the flow go through the interstitial of the big gap that has a big area. So that's why model A and model B still question the question mark here. Then later we need a DS type model to get the detailed, like we deep into each particle to see what's the drag force distribution. That's comes with Professor my supervisor team use lattice Boltzmann model to get more detailed. This model quite complex in a certain area. This is still an area not finished. I saw from in China we have still a number of groups working in this area.
Okay, this is clear. Also, I have some questions for your presentation. Yeah. So in your case, you also mentioned the modified model B. Which parameter or terms you modified? I remember, the modified model
A. You know, if the shared, if the pressure, you see here very interesting.
This one.
the pressure term is we call D, dynamic pressure. That's by drag.
Okay.
If we use a traditional CFD, only one pressure gradient, but we have different particles. If you see based on the volume fraction, that means each particle contribute the drag by its volume, like a buoyancy force, like a particle in the water. It's as the static buoyancy force, but the contribution of the PD, this dynamic drag, because in relative velocity, it's contribute more by small particles contribute more than others. So we need a small particle share more by what? Why we saw by because the drag force mainly why small particle get large drag than the large particle, because it's the same volume fraction, but it gets more surface area. So we share by the surface area. Then they get the modified model A, get better results close to model B and close to experiment.
Okay, thank you. Now, I have also another question. Very interesting. You talk about the collaboration with Qinggong Wang. You mentioned, CFD DM hybrid model for whole particle segregations. That's very intriguing. And can you give some more detail about how to couple these two models? And also, this is a small scale or large scale for this process?
Okay, probably. I just share again this one. This one is very just so actually since I joined Cyro, it's in my mind many years, but one is no resources and another is no time to do that. This is a co-beneficial project. It's from we call in China 973 project. And then this linked with Qinggong Wang is Tsinghua University with Professor with Professor Li, Junfu Li.
Junfu Li.
I work also with the China Mining University with Professor Zhao, and we use the DM. This one. The only difficulty is we know the TOEFL model for the dense media easy, and DM for the coarse particle easy, but the coupling between the coarse particle and the continuous solid is another difficulty. And with gas needed. And the thing that we use what? We just use the traditional we drag force, but the drag force for the particle and air use a similar formula with the particle and the continuous fluid phase. This is the area in 2019 when I visited you want to further to do something is how to validate out how to improve the drag between coarse particle and fine powder. This is the one area still challenging me. The meanwhile, I must probably use a few words mention. I don't have time. When last time I visited Professor Junfu Wang is from IPE, Institute of Process Engineering. He proposed another approach, and we call coarse grain model and the DEM. That means the bottom, the continuous fine powder, he use coarse grain model, use barracuda type model, the particle in cell. Then they coupled with the coarse particle. That model, another challenge is how to the interaction between the coarse particle and the continuous particles. This is another challenge. They just use the traditional contact model, not work. I propose a ghost cell model. That means we still treat the particle in cell with continuous approach, and still, very interesting. There'll be a lot of work to do in this area.
Yes, okay. Thank you.
Yeah,
maybe I have the last question, the last one. And then in the real industry process, maybe we consider 2 scales, one in time scales, maybe sometimes they are very long, for example, 1 year, 2 years. Also the large scale, also dimension very large, for example, maybe 100 meters long. In the simulation, how do you consider or balance the 2 scales? Consider different models, for example, DNS, CFD, DM, also MP, PC method. Maybe that different approach.
Yeah, this is use aluminum cell or flotation cell is the actually we can this 2-type model, the multi-scale we call concurrent. That means in one simulation we both consider like this one, both consider the cost of the particles and the container to from a hybrid couple. Another is we have loose coupling. Loose coupling is like the flotation. We based on the based on the use the available models to assess the performance of each assessment of the performance of collection efficiency or the flotation efficiency. Meanwhile, the different terms, quite empirical, we develop the detailed particle bubble collision model to improve it. You see, once we get the improvement, use improvement to further improve model, but we cannot wait for the micro model readily available to do industrial applications.
Okay, thank you very much. Due to the time issue, so maybe we can talk later, if face to face, maybe.
Yes.
Yeah.
Okay.